for computational mechanics, and this is we have a national chapter and we have a local student chapter at Berkeley. So we are a local student chapter, and today we are going to have a Dr. Claudio Perez talking about his work related to high performance computing and finite element analysis. Before going further, let me briefly introduce Dr. Claudio Perez. Let me pull up.
Not doctor yet.
But almost there.
Yeah.
Yeah, got it. So Claudio is a PhD student specializing in scientific computing. His research focuses on computational mechanics and structural health monitoring, with a particular interest in differential computing. As a core member of their lab, Claudio has designed the with a particular interest in differential computing as a core member of their lab, Claudio has designed the computational backend and the curated software ecosystem employed by the research lab to execute large-scale regional models of civil infrastructure. Claudio is an active member of Kara Python package for nonlinear finite element method. So without further ado, please, Claudio.
Thanks. Hi everyone. So welcome to the first MechBytes seminar. So I'll start with just a little bit about what USACM at Berkeley is and what the MechBytes seminars are and what we hope to cultivate with them. So we're a student chapter of the United States Association for Computational Mechanics. And our objective is to just kind of foster a collaborative environment in the university. And to just like communicate what we're up to, what kind of research we're doing, and the different methods we're looking into, and just kind of foster connectivity in the university across different departments. So first, also special thanks to Shren. None of this would be possible without Shren. Shren was he took initiative to start the chapter, and continues to do a whole lot of work. So thank you, Shren, for making this possible. I think this is great. Okay, so a little bit about me. My research is mostly on modeling nonlinear rods, so both accounting for inelasticity and finite deformation. And I implement most of my work in the open source software package Kara, which is derived from OpenC's, which is a very well-known finite element framework. But which tends to be sometimes obtuse. So in Kara, we are extensively refactoring the front end and making it very usable from Python. And it's an extremely high performance platform and all open source and documentation under development. And then this is all applied to structural health monitoring. So in the BRACE2 project, we have the Department of Transportation has a bunch of bridges with sensors. And our objective is in real time, take this sensor data when an earthquake happens and try to assess the health of the structure. So that's where my research goes towards. So what I'm going to be talking about today is just sharing a little bit of my observations from this research, particularly for high performance computing, and some things I've been able to do to squeeze performance out of the finite element procedures. I'll start with some computing concepts from operating systems, and then recount the general, like what's happening in nonlinear finite element analysis, and then talk a little bit about some things that yield meaningful optimizations. But first, like short survey. How many people here are comfortable with like the structure of code for nonlinear finite element analysis? Okay. And like just generally like the procedures that are happening in the background, like there's a residual being solved for and stuff. Okay. And who here works with low level language like Fortran, C or C++? Okay, so anyone that who has interest in it? Okay. Okay, I'll begin by reviewing some like pretty fundamental concepts from just general operating systems, which are incredibly useful to have a grip of for implementing finite element analysis and nonlinear analysis. So in general, with operating systems, theory of operating systems has four fundamental abstractions. And so this is covered like in an operating systems class. First, you have a process, and this is what is started. This is how like the operating system is representing a program that you run. And a process is given its own address space for memory. So like an array of addresses, integer addresses for memory. And then it has one or more threads. And then a thread is an execution context. It's something that it's like a representation of something you can put on a CPU, like a sequence of CPU instructions. So your program can spawn like a different sets of CPU instructions that might be run concurrently. And then there's this idea of privileged instructions. So nowadays, every CPU, the instructions that are available to it are split in half, or not in half. But there's two types of instructions. There's like the unprivileged instructions, which is like an instruction that might add two floats or like simple operations, like the very basic arithmetic, essentially. And then there's privileged instructions, which are instructions that tell the CPU to like communicate with hardware on the computer, or like communicate on networks, allocate memory. And these can only be run by the operating system. So when when a computer starts, it's first put into privilege mode. So there's like a toggle on every CPU for what mode it's in. It's booted into the privilege mode, and then the operating system, which is just a program, is set to run. And then the operating system is going to go through and start invoking different programs. And when it invokes the programs, it switches the CPU into the unprivileged mode. So every program that's not the operating system program is running in unprivileged mode. And then there's address spaces. So when the OS, the operating system, invokes a process or starts a program, it sets up the address space. And I'll get into more details about that later. Okay, so processes and threads, a little more detail on this. A process has its own address space, like I mentioned, and nothing can touch its address space. So everything that you're writing, like every variable you have in your program, can't be touched by any other process, but the process that you're running in. So if you want to send data or variables or matrices or anything to any other process, you have to do it through what's called inter-process communication, which is pretty hairy. You can't just like, there's no way for another process to access your variables that you've coded. And so the standard for doing this is a set of functions that are defined by something called MPI. And they define functions that you can invoke that are going to help with passing this data between different processes. And then a thread has its own, they're spawned from a process, and they can access any of the addresses of that process. So if you want to share data between threads, the threads can just access the variables directly. And you have to be careful that you're not like clobbering things, that you're not like writing to variables at bad times. So it's on you to manage that you're doing that properly, because you have free access to all the addresses. But that's extremely fast writing to an address. It's just storing variables. So to spawn processes, you would typically use either your operating system's threads, or OpenMP, which is another open source specification of functions to spawn threads. So the most control you'll get is through operating system threads. So your operating system will have a set of functions for spawning threads. And then also C++ has a standard set of functions that wrap those, which is also useful. So yeah, threads are extremely important. Then we have scheduling. So the operating system, the CPU starts up, the operating system goes through, invokes a bunch of processes. It probably invokes like the shell process, and then your shell process is going to tell the operating system to invoke the programs that you tell the shell to invoke. And at any given second, there's a million processes running on a computer, and they're all being switched in and out in very small time intervals. So when your program runs, and this, I'm sure everyone knows this, maybe, it's constantly stopping and starting. So the operating system is going to give it like a series of milliseconds that it's allowed to execute its instructions, and then it's going to stop it, store its state, and swap another program in. And so that's scheduling. Yeah. So I think I already explained the modes of a CPU. But this becomes very important because in any computation you're doing, you're going to need to use unprivileged and privileged instructions. And to do that, you have to go through what's called a system call. So whatever language you're writing in is going to expose some standard library functions to you that wrap what's called system calls. So these are some common ones from C, like reading to a file, reading from a file, writing to a file, allocating memory, spawning threads, spawning processes, all these things. So what's important here is that like whenever you're invoking these behaviors from your program, it's really useful to know that what you're actually doing is you're kind of giving up whatever time you have on the CPU. Like so if your program is executing a series of instructions, the operating system gave you a set amount of time to run on the CPU. But at the point that you need to do something that requires privilege, you give up any of the remaining time that the operating system gave you, and you give it back to the operating system, and the operating system puts you back in line with all the other programs that are running. And then the operating system goes in and does these things on your behalf. And that's extremely costly. So this is something that like should be avoided at all costs. Like whenever your program was given an amount of time on the CPU, you want to hang on to it for dear life, and you want to get that whole amount of time. You don't want to give it up prematurely. So that's the first cost, is you're giving up time that you were given on the CPU. And then also that process of like, so when you give up the CPU and another program gets put in its place, this is a very costly process. The operating system has to go in and restore all the variables of the program that it's now invoking, has to save the whole state of your program, like all the variables that you have stored and everything. And this is happening a million times behind the scenes. With programming, well, okay, yeah, and then your cache is polluted. So with let's see, so sorry, I'm kind of like jumping a little bit. So with when your program's running, I didn't explain caches, but is everyone comfortable with caching, CPU caches? So like as your program is running, the CPU is figuring out what to keep close to it. And if it ever, like anytime you have to access something that the CPU didn't like bring close to itself, it's going to check if it's nearby. And if it misses, it goes and checks somewhere else and then checks somewhere else. And this is like makes it very costly. And this is happening every time like you read a variable. So if you have like X set to 1 and integer X1, integer Y1, and you add them together, the values for X and Y have to be retrieved. And if it's not in cache, it's going to go on a goose chase for where that value is. So nowadays with modern processors, one of the most important things is to write your program in a way that the cache stays hot, like it tends to have the variables you're working with. Context switching is going to wipe your cache. And there are other things to do to keep the cache hot that we'll get into. There was something else I wanted to bring up. Oh, so all this is happening in any programming language, but in something like Python, you have like almost no control over context switches because like every variable in Python is on the heap, which is I guess I'll get into it. So okay, the stack and heap. So all the addresses your program gets, your program starts with a fixed set of addresses, and when it needs more memory, it has to request it from the operating system with a system call. So it has to clock out of the CPU, it has to forfeit its time and request memory. In dynamic languages and interpretive languages, generally every variable is like that. And the interpreter is going to try to like internally minimize requests for memory. So it's going to ask for bigger blocks of memory than you're actually like using from Python. But that just makes it extremely unpredictable when these system calls are going to be invoked. If you're writing in C, C++, or Fortran, you'll know exactly when that's happening. So the stack is all the memory that your program was given first when it was invoked. And anything that you know the size of at compile time gets essentially to live in the stack. And so anything that's allocated on the stack is basically free. All it costs is the CPU is just going to increment a counter that counts like where your memory currently is. And then heap memory, like dynamic memory, requires a whole system call to get. The thing about being freed automatically and manually is kind of becoming pretty obsolete these days. Even in low-level languages, you tend to not have to worry about it if you're using modern features, and it's generally at no cost. Like this syntax is like usually you're not gonna have to do something like that. Okay. Okay, caching. I should have put this earlier. Caching, you want to keep the cache hot. Okay, so any questions? Is this just kind of redundant for everybody or
Well, I do have one question regarding this part. Because you said like the read and write is will interrupt the system calls. So does that mean like if I have a program and I have so many read and write sentences in the program, that means the program will be terminated for multiple times and saved in the memory and then will be retrieved later after the read and write.
yeah. Yeah. So every time that's why, well, so reading and writing to files is an incredibly slow thing for two reasons. First, you're context switching a bunch. You're giving up a bunch of your CPU and giving back control to the operating system because the operating system's doing that for you. And then also you run into the physics of the memory drive. Like reading and writing to an actual drive is just costly. It's a slow thing physically to do. And it's a lot. So like files are stored on hardware wise, much slower hardware than your RAM is. So like writing variables to like values into variables in your programming language is happening on the fastest memory your computer has. Whereas writing data into persistent files is writing onto very physically slow hardware. Okay, so I think this is probably going to be redundant for most people, but just briefly recalling that in a nonlinear finite element analysis, we have this residual that we're solving for zero, and we're doing a bunch of Newton-Raphson iterations. So we're in like factoring a matrix on every iteration. This is generally going to come like inverting K. So at each iteration, you invert K to get this increment, solving like against the current value of the residual. Inverting K, performing that solve is like usually just going to completely dominate everything, but you can still squeeze a lot of performance out of other areas, especially if there's anything slow that you're doing in those. So the main other place you would have performance problems is in assembling K, which is the assembly procedure, which is looping over all your elements and adding in their contribution to the stiffness matrix. And then every element is doing something that looks like this, usually. So like beams and shells and quads, all general, like almost any finite element analysis is going to end up a procedure like this. So then optimizing things. The first step is always profile. Premature optimization is like the worst thing you can do. So always never optimize anything before you profile your code. C-Lion is an IDE that has built-in profiling that's now free. It's like this year at some point they made it free and it's pretty helpful, especially on Mac OS. In Linux, there's a lot of great things on the command line interface. So stick with that and just usually it's like pretty easy to find profilers for that. And on Windows, try to avoid Windows. It's a problem, but I think Visual Studio will probably take care of it for you. It probably has a profiler built in. I don't know. I avoid Visual Studio at all costs. Okay, so local arrays. So in a finite element implementation, you pretty much always know the size of all the arrays that are used inside the element at compile time. So put them on the stack, use stack allocation, make sure that whatever programming language you're in, that these are being put on the stack. So I don't know much about where Fortran is these days. I don't know, but in C++, okay, so I didn't fill out this slide, I ran out of time, but C++ nowadays, and especially recently, they've been standardizing something called return value optimization, where if you return like matrices and vectors just directly from a function, in the past and up until pretty recently, that would mean that inside the function, say like you have a function that returns a matrix. Trying to think of an example. So, like a material. A material returns a tangent, like a 3 by 3 or something if you're in plane stress. In the past, like the materials, the function that populates that material, the tangent, it would populate it on the function call stack, and then it would have to copy it out to wherever the return is. So I guess this is a good example. So if you have something like this, where your material, you retrieve its tangent, when this function is being invoked, in the past, it would be forming the whole matrix there and then moving it to wherever the stack is for this function, the get at tangent. So this is an example of like just an element adding its tangent component to a global system. But nowadays, C++, if you do things right, it's going to just build this in place and not have any copies. This is called RVO, and like is a pretty significant thing for performance. So yeah, so if you have small matrices and functions and stuff, return them by value. Don't do like wonky static allocations or in place things. You can return by value from C++. And then also templates in C++. Is anyone here comfortable with templates in C++? So templates are your friend. Templates are like completely essential. Template like anything that you can. So anything that looks like it might be variable size. Like if you want to implement a quad with variable number of nodes, you can probably template the number of nodes, which this is just like a rough pseudocode demonstration of that also. And then yeah, so that kind of wraps everything up. In summary, the things I've found that give noticeable improvements is templating things everywhere possible, returning by value, stay in user space, don't do anything that's going to make a system call. And yeah, and then also in this example, so this for loop in every iteration is building a D and a B matrix. And it might look like this is wasteful with memory, but if you have cheap matrices, like well-implemented matrices, there's going to be no reallocation here, basically. Like you don't have to be messy about like defining it once in an outer scope. You can just scope everything properly. Deleting this and reallocating it on every iteration is going to be completely optimized away by the compiler. And leads to much more readable code. So yeah, I think that's most of the things I've found to be pretty significant for getting some performance out of finite element implementations. And then, yeah, in conclusion, you can, everyone feel free to email me about anything with any questions. And also, the USACM GitHub account is this. And we'll also update it with a website link that's under development. And yeah, we hope to foster community, share a lot of code, and yeah, just a lot of communication with what everyone's up to. And that's about it. Any questions?
Well, thank you again for this fascinating presentation. Any questions? Yes?
Questions. So since we're working with nonlinear FE, right? My most bottleneck is actually to really assemble huge matrices. I mean, solving matrices, I think recently I just use like whatever solver you have. And,
Yeah.
It's generally fast, but to assemble it smartly, it's really a game changer if you can do it online, right?
Yeah.
Any advice on your end, like how you can find strategy to actually assemble big matrices, sparse matrix, right, in a most efficient way?
That's a really good question. So it's very specific to what you're using for your solvers, right? Like if you use PETC, because like you're gonna abstract away the level between the assembly and then populating to send out, because you're gonna outsource all the solving, like you said. But it'll depend a lot on that interface for how optimally you can do that assembly. Like what kind of API you're given to populate the matrix that you're going to send to the solver. But yeah, I've had a lot of thoughts. Currently, what I inherited from OpenSeas, I think, is at least for the time reasonably clever and all right. But I have a lot of ideas on different things. Like what Yeah, that's a great question, but hard to discuss without like looking at some code together. I'd love to see what kind of code you have and show you some of the ideas I have. Like there uh yeah, it's definitely important.
Well, I mean, it's just the current level. But I think, you know, when I see people can smartly, for example, you're probably familiar with the B-free approach. So basically matrix free approach. So there is no intermediate matrices. You can directly jump to the each cost point and take some stuff out. Whatever. And then you can actually make this nonlinear finite element to a GPU basically. So you can sort of parallelize this into a GPU set.
But I imagine this is for an iterative solver, right? Like this you wouldn't be able to do on a direct solver.
That's right.
That is very interesting. So the problems that we tend to have in civil engineering don't get to the size where iterative solvers beat out direct solvers. Because civil engineering, it's a lot of frame elements, and frame elements are usually pretty high order. And so you're not discretizing it insanely fine. But yeah, I think definitely if you're up to like a couple 100,000 degrees of freedom, that's probably the only way.
Even like if you're dealing with a well-conditioned system, but like if you're dealing with like any type of projectiles where you have like singular matrices or like close to singular matrices, I think direct solver will sometimes be a little bit more challenging in the sense that it requires certain conditions to actually.
Yeah. Yeah, that's also interesting. I tended to deal with that with the algorithm, so like switching to modified Newton and things like that. And line search is like amazing. But yeah, that's another good point. Um I was thinking of something along those lines. Uh but yeah, that's all very interesting. I'm just trying to gather like so many thoughts this brings up. Um, yeah, one of the surprising observations I've been making lately is that on a Mac or on an Intel CPU, the law pack is usually so optimized that it goes further than you would think. It beats out mumps and ump pack for longer than you would think. Like just like a band general law pack kills it often on a like if you have MKL or Apple Accelerate. Um, on Linux, I haven't found a BLAS that or a LAPACK that beats mumps or UMPAC as well. Uh, yeah. Any other? We should it would be interesting to meet sometime and look over how you're assembling things.
Yeah. I mean, like, I think my condition or some of us here, we're working with like a little bit like crazy system on matrix to solve. And it's not always easy. I mean, especially if you're dealing with like local intrusions and you have things that instability where like
Yeah.
this is like stuff that people in the fluid mechanics are all look into. Generally solving is, I mean, I would just say even solving is difficult, but I think solving is still fast. It's when the mathematicians were creating the solvers routine like fancy, so doing exercise, right?
Yeah.
But somehow to supply that to solve, we have to assemble a matrix, and this matrix assembly is sometimes even I don't know if you've done this. That's because doing it smart is going to change your speed up. If you profile, right, you can see that the matrix assembly normally takes like more than like 60% of your computation.
That's interesting. So in the problems that I tend to run at, it's not like that. It tends to be dominated by the solver.
How big is your system?
I've seen this up to about like 400,000 degrees of freedom. I haven't gone bigger than that. What are
Well,
your
it's
systems
about
usually?
the same. Because so 400,000 is in 3D.
Yeah.
I deal with like maybe about 200K or 200K, but just multiply that by 4, so 800.
Why by 4?
I mean, like, because I have 3 displacement and 1 pressure, or even like by 7 if you have like displacement, and pressure or something. So it's like a block matrix is like a huge system. So it's not only displacement. So we have other constraints.
Yeah. Um, yeah, but 400,000, I mean degrees of freedom. Generally.
I mean, that's good. I mean, it would be interesting to see how you would assemble your matrix, especially.
Yeah, we have a pool, like a pool of so apart from the element assembles into a space that is pre-allocated in a pool of space for the stiffness. So the whole amount of memory is like very small for the element stiffnesses. But managing the pool is kind of hairy, and I don't know that it's the best way.
But you also use MPI for this, right? That means that for each rank you have to assemble first so a simplest, like a smaller matrix, sub matrices. Like say you have 4 rank, you have 4 of them. And then PETC will do the automatic matrix assembly for the entire system. So
I actually don't do too much MPI. So like I lately just been threading and so like the assembly I haven't done much parallelism in. That's something I'd like to go and do. But typically I leave the parallelism to the solver and then also the element states. So when running, like we do a lot of, for inelasticity, we do a lot of mixed formulations that have a lot of integration points. So like our models in structural engineering tend to have fewer degrees of freedom and more integration points. And so we'll thread the integration of the element in a pool of threads. Yeah.
Okay. Any other questions? Okay, maybe thank you again for this presentation. Yeah, so now we are jumping to the coffee hours. Please help yourself to get some food, food, drinks, and coffee. Yeah, please feel free to stay or feel free to grab some food with you.